Hello everyone, so welcome to week 3. So today we'll be starting with discussion on how do you represent a word in NLP, and we will be starting to use deep learning techniques for this. So this lecture is word representation. What we'll cover in this lecture is how do you represent a word in language, so typically using the deep learning methods. So we'll briefly describe the genesis of this, that is a distributional hypothesis, and how it leads to the latest developments in word embeddings. We'll talk about sparse versus dense vectors and which one to use for machine learning, and we'll start talking about reasoning with word vectors, and we'll continue this discussion in the next lecture on how do you learn these word vectors. Okay. So now typically how do you represent a word, right? So because if you want to apply NLP or machine learning for a task in NLP, the input will be the language, text and sentence. So you individually need another word. You have to feed that word to the machine learning model, right? So you need to have some representation to that. So classically, what is the representation that is given? So one way is that suppose you have vocabulary of size V. Now you will say, okay, I'll index each word in the vocabulary, right? Each word has an index in the vocabulary. Now I will just put a 1 in that index and I'll put 0 everywhere else, right? So that ensures that every word has a unique representation. So for example, so suppose you have two words, motel and hotel, and let's say they are put in the lexicographical order. So hotel will come before motel. So now what you would do, suppose this was the index of the word hotel and this was the index of the word motel, right? And you have put the 1 in the corresponding indices and everywhere else you have put a 0. And this particular representation is called a one-hot representation. It's 1 in only one dimension, everything where else it's a 0. And what is the size of this vector? This is as long as the size of your vocabulary. So it can be very high, maybe 500,000 or even more, depending on your vocabulary size. Now, what is the issue with this representation? Right? Immediately you can see that like these two words are very similar, motel and hotel. They are having very similar meanings, but in this particular representation, if you do an AND of these vectors, you will get a 0, as if they are completely orthogonal vectors. So for example, suppose you are doing search for Baltimore motel, and one of the possible web page where the answer is mentions Baltimore hotel, but you won't be able to find similarity using this representation. You will say, okay, motel and hotel are two different things altogether. Their similarity as per this vector is 0. Okay. So what it means is that in this one-hot representation, there is no natural notion of similarity between words. Right? And also they are huge, like 500,000 dimensions, because you understand now with the deep learning concepts that if your input is very long, having a very long dimension, very lengthy dimension, accordingly your matrix will also become very lengthy, because you have to multiply this whole input to some matrix to get some hidden representation. So that means you would prefer to use shorter vectors. So I want to use shorter vectors, and I want some way in which I can define similarity between vectors. So representation that encodes a similarity between the words. Now how do I achieve that? Now that's where the distributional hypothesis comes in. So Wittgenstein was one of the first person who talked about it. So the meaning of a word is its use in the language, right? You know a word by how it is used in the language. And there are many other linguistics who talked about it. For example, Jallik Harris says, if A and B, they are two words, have almost identical environments, we see that they are synonyms. So what do I mean by environment? That is the words around them. So if you look a lot of data and see what are the words typically come with these words, right, in different pattern, different occurrences. See, the word A may have occurred multiple times in the corpus. What are the surrounding words of A, right? Similarly, you would have the word B coming in the corpus. What are the surrounding words of B? So, if the surrounding words are similar, maybe A and B are also similar, they are occurring in similar environments. Now, just to give more context to this, just to take an example. So, you see this recent English borrowing ong choi, right, and you suppose you see these sentences, ong choi is delicious, so with garlic, ong choi is superb over rice, leaves with salty sausage, and so on. Now, given these sentences, you would start understanding a bit about what is ong choi, right. Why? Because you would have also seen something like spinach in a very similar context, right. You would have seen cart stems and leaves are delicious. You would have seen collard greens and other salty leafy greens. So, you start thinking like, oh, it is some sort of a leafy vegetable similar to spinach and other such occurrences. So, you would say, okay, yeah, ong choi is a leafy green like a spinach and other things that I have seen in similar context, right. That is how typically we understand the words also, and we have seen similar context around ong choi and other synonyms, right. So, and that is what ong choi is, water spinach, right. So, you get this idea by looking at the context in which the word occurs. Now, can we generalize this idea to say, okay, every word we look at the distributional pattern, like what are the other words it occurs with, and use that to denote this particular word's meaning. So, we will come back to that. So, finally, what you want to do? So, you want to represent a word by using a vector, right. And what is our criteria? So, similar words should be nearby in the semantic space. They should have similar distributional patterns, similar vectors. Similar words should have similar vectors. And we want to build this space automatically by seeing which words are nearby in the data, right. Something like this. So, I would like to see, okay, things like very good, amazing, terrific, they were coming very close to each other and they are distant from other cluster like not good, dislike, bad, incredibly, and so on, incredibly bad, worst, worse, and so on, right. We would like to see some sort of clusters emerging by this notion of similarity between vectors. Okay. So, what we will do finally then? So, the meaning of a word is nothing but this vector, and that will encode similarity notion between words, right. And this is called an embedding because you are embedding that into a space, right. And that has become the standard way of representing the meaning in NLP, right. So, you would see all modern NLP algorithms, they use embeddings as the representation of word meaning, and this captures very fine-grained model of meaning for similarity. So, now the question may arise like, why do we need vectors, right? Why do you want to use vectors? So, think about some classical machine learning algorithms. So, what would you do? So, you would typically encode various features that you want to use. So, for example, your feature can be like, one of the feature is the previous word was terrible. I mean, the previous word to this position was terrible. Suppose you are doing named entity recognition for a word, your feature is the previous word is terrible. Fine, but it means that this requires exact same word to present in the test data. So, in the test data again you have another word and the previous word to that is terrible, your feature will click, right. But what if you got some other synonym of terrible? What if you got dreadful or something different, right? So, what would happen? So, it won't trigger, right. It won't trigger for any other synonym because it needs the exact same word. Now, what would happen with vectors? So, now what would happen? We will not encode the word directly, we will not match the word directly. Instead, what I will say, the previous word, so this whole dimension, this is the embedding dimension, is terrible. So, I will encode the embedding of terrible. So, I will say, okay, I will have a vector like 35, 22, 17. So, these are some dimensions of my feature vector. Now, even if a similar word occurs instead of this, it would have very similar vector, right. So, what would happen? Even if you have learned for this, it would be applicable even for a similar vector. Whatever you have learned for this will be applicable to a similar vector. That was not the case when you were encoding words directly, not as features as one hot. Okay. So, you can generalize to similar but unseen words, right. That will be the the main point that you would gain by using word vectors. That you will generalize to similar words, right? Your learnings. So now, how do you encode similarity? So one way is you can use distributional vectors. You capture distributional patterns. Right? So this is one algorithm for computing distributional vectors. So what you can do? So you have some target words, and that you want to build the word vector for, and what you do to count co-occurrence, like what are the distributions, you define some context window. Let's say what are the number of words surrounding your target words. So it can be like in the same sentence, if two words occur, I will call them as co-occurring. If they occur within 4 words of each other, I can call them co-occurring. So context window can be many things. It can be whole document, paragraph, sentence, even like -4 words, +4 words to the center word. So you can define this context window in various different ways. And then once you define your context window, you can count how many times a particular pair of words have co-occurred in the entire data, right? And this you can compute in a single pass over the corpus, right? And once you have computed your co-occurrence matrix, you can build a vector of these co-occurrence count. And you can see if two words have very similar distributions, you can call them similar. Like take this example, we have a small data set with 6 sentences, okay, and let's say we want to find the vectors for some targets like automobile, car, soccer and football, and in general we define all the words as context, but just to convey this point, we have taken 7 words: wheel, transport, passenger, tournament, London, goal and match. Right. So what I will do next, and let's say my context window is the entire sentence. Sentence is my context window. So now I will see wherever automobile and wheel have co-occurred, how many times in a sentence. And suppose I am doing the lemmatization and all, so I will find automobile and wheel have co-occurred once in a sentence. Similarly, football and passenger would have co-occurred somewhere. So passenger and football. So that's why you have football and passenger. Football and tournament would have co-occurred somewhere. Football tournament. Right? That's why you have this one, and so on. So you get this distributional vectors. So now what it is telling me, this is the distributional vector for automobile, and this is the distribution vector for car. And I can now see, and this is for football, and just from this I can see that the distribution vectors for automobile and car are very similar, and that of soccer and football are very similar, but among them they are distant, right? They are different. So this simple distributional similarity, distributional vectors also captures the notion of similarity, right? I can say that automobile and car are similar and soccer and football are similar. I can also compute their similarity as a quantity by taking the dot product of these vectors. So I can take dot product, I will say 1 times 1 plus 1 times 2 plus 1 times 1. So automobile dot car is 4, soccer dot football is 1 plus 1 plus 2 plus 1, 5, automobile dot soccer is 0. So clearly you see automobile dot car has a very high similarity, soccer dot football has a very high similarity, right? So this again captures notion of similarity. I can do more slightly better, I can use cosine similarity instead of this, and this will give me a range between -1 to 1. In this case, because they are all non-negative numbers, this will be between 0 and 1. Okay. So I can capture similarity by this vectors, right? This is a very this was a very interesting notion, and that remained so till the word embeddings, and even word embeddings use a lot from this idea. Now you can also do something more, something even better than this. So you can say, okay, I have this vectors, but I am giving a weight of 1 and 1 to each with co-occurrence. Are the weights good enough, or can I give a function of these weights? So people have found out that okay, you can do even better. For example, take this intuition. So suppose you have 2 words, dog and small, and they have co-occurred 855 times. Frequency of 1 and 2 co-occurring 855. Other hand, you have dog and domesticated, they have co-occurred 29 times, right? So by the current matrix, I will say this has a higher number or higher association, right? Dog and small compared to dog and domesticated. But is that really so? So you look deeper and find out the frequency of the individual words. You say, okay, dog has a frequency of 33,000 plus, that is common, but small has a frequency of 490,000 compared to domesticated with a frequency of 918, right. So, now once you look at these frequencies, you get some idea that okay, small was anyway a very common word, so it would have co-occurred in general, right. So, its co-occurring with doc 855 times may not be as interesting as a rare word like domesticated occurring 29 times with it, right. So, how do you capture this notion quantitatively? So, that is where you use the some association measures. So, they are used to give some weightage to contexts that are more significantly associated with the target word. Okay. So, the less frequent the target and context elements are, you give a higher weightage, right. So, and there are various measures for this like mutual information, log likelihood ratio and all. So, what happens in mutual information? So, the metric is, suppose I have two words W1 W2 and this is their frequencies of co-occurring and these are the individual frequencies. So, PMI is defined as, so log of what is the probability of their actual co-occurrence. So, this is whatever I observed. So, probability of their actual co-occurrence divided by what would have been the probability of their co-occurrence if they were independent. So, if they were independent, so what would have been their probability? So, if they were independent, I mean you will simply multiply the individual probability. So, you will simply count it as probability corpus W1 W2 divided by probability corpus W1, the independent events. So, joint probability multiplication, right, and that is where you get this PMI and you took a log measure, right. So, typically it tells you this is the probability with which they would have co-occurred anyway if they were random words, right. Now, this tells you what is the probability with which they have actually co-occurred. So, if this probability is higher than the random probability, that means you have some association, right, and that is what it captures by log. So, typically because you are using log, if it is greater than 1, then only you will get a positive value, and sometimes people use PPMI, that is positive PMI. So, where the negative values are converted to 0. So, you only take the positive part, okay. And individual probabilities are easy to get, frequency of the word in the corpus, the number of tokens times this token has occurred, divided by the number of documents in the corpus. So, if you actually work out this formula, simply like n times frequency W1 W2 divided by frequency W1 times frequency W2, and then you take a log with base 2 or 10, right, whichever you want to use, okay, and that defines another measure, right, point wise mutual information measure, and this is very popular in the literature. So, that means that rather than using just simple count, I can also give some interesting measures, association measures like PMI for this, right. Similarly, other way you can compute distributional vectors is just use the document as context. That is, if you have a large corpus, you can find given each word which all documents it has occurred in, right. So, for example, you have 10 documents here, against occurred in 1, 3 and 2, and some age occurs in 1, 3, 1 and 2, and in D4, D6, D7 and D9, and D9 occurred 4 number of times and so on. So, you have these count vectors, right, each word how many times it has occurred in a document. You can find out similarity between these vectors and say, okay, if two words have occurred in similar documents, they are similar words, okay. So, that is another way, and you can also weight them. So, very popular weighting scheme for these count vectors called TF-IDF, term frequency inverse document frequency. So, what do you do? So, you say, okay, how many times a word has occurred in the document, so its actual frequency. So, ith word occurring in the, so ith document, jth word. So, you say, okay, how many times the word j has occurred in the ith document. So, that we saw in the count here like 3 times, 2 times. So, I have the count in the document, word frequency, and say, okay, how many words have occurred in the document. If there are more words, you will give a smaller weight. So, it will be inversely proportional to the document length, and if this word is a rare word, I will give a high weightage. If this was a very common word, I will give a low weightage, right, because it is a common word, it will anyway occur everywhere. So, it is inversely proportional to the number of documents in which this word occurred, called document frequency. and that is how you define this TF-IDF, term frequency times inverse document frequency. So, number of times it has occurred, the count in the document, times log of number of total documents divided by number of documents in which it has occurred. So, if nj is high, it is a common word, this would be roughly close to, the ratio will be roughly close to 1 and log of 1 will be 0, you will get a 0 weightage. But if nj is small, it is a rare word, you will get a high weightage. So, this is the intuition for TF-IDF, that can be another measure. So, that means I have now multiple possibilities of doing the vectors, right. But the vectors we talked about, whether they are one hot or they are distributional vectors, whether it is PMI, TF-IDF, they all have this problem that they are very long vectors, right. Because think about PMI, you still have to count word across all the words as context, right. So, this dimension will be still your vocabulary size. Same happens with TF-IDF, your dimension will be the number of documents in the corpus, that will be again huge, right. So, they have huge dimensions, and both of them are sparse, like they are, most of the elements will still remain 0. Now, alternative to that is, can we use vectors which are shorter in length, say 50,000, and they are dense, they are not like sparse vectors, most elements are non-zero, and that is where we use the embeddings, the dense vectors. Now, short vectors, the help that they do for us is that now the input to my machine learning model becomes smaller, the dimensions become small. So, it is easier to use them as features, because you have fewer weights in the model, and they typically generalize well, because synonyms will have similar vectors. So, they are better at capturing synonymy, like the word car and automobile typically would have very similar vectors, while in one hot they may be very different, they would be very different. Right. So, distribution vectors try to take care of this problem, but they still suffer from very large dimensions. Now, how do you get the short vectors, right? So, in the literature again there are many ways. So, even before word embeddings came in, there was latent semantic analysis or singular value decomposition method proposed in 1990. Okay. So, that said that you can use this term document matrix and do some nice linear algebra on that, and you will get low dimension vectors for both words and documents, right. So, you can read on that. So, it is a very interesting concept, and this also gives you some sort of embedding for both words and documents. But what became popular is this word2vec, the word embeddings. So, this was many variations, skipgram and CBOW, and also we have glove vectors. So, they are the models that we will talk about now, and these will give you static embeddings. For each word you will have only one embedding. There are methods that later on got developed that will give you contextual embedding. For each word, in every context you have a unique embedding, and these will be the models we will cover later in the course, like Elmo and BERT. Okay. So, they will compute distinct embeddings for each different context for the same word. Right. So, we will talk about CBOW and word2vec. So, what happens in word2vec? So, instead of counting how often each word occurs near a apricot that you do in distributional vectors, you do a classification task, that is this word likely to show up near the word apricot, right. So, you change the problem formulation, rather than counting you say, okay, what is the probability of this word occurring near this. And finally, we do not care about this task of prediction, this is only used as a self supervision, you are only using it to learn the vectors, later on you do not need this task. So, this is a first example of self supervised learning that we will see. You do not need any additional labels, just take a lot of data on the web and you can apply this method. You can see, okay, given a word, what is the probability of this word occurring in the context, right, and use that to update the word vectors until you are satisfied, right, after sufficient number of epochs. And this is the idea of self supervision. So, a word C that occurs near apricot in the corpus actually acts as the gold correct answer, right. You do not have to manually label this. This is treated as the gold correct answer for supervised learning. No need for human labels, and like this idea started from Benjo's paper 2003. Colobert 2011 also proposed something similar. So, what will we do in this word2vec? So, let us say we have we'll take a vector with several hundred dimensions. So let's say 300 was a typical number, and you will represent a word by a distribution, right, of weights across these elements. So you have say 300 dimension, and each dimension has some weight 0.25, 0.7, minus 0.2, and so on, right. And each vector is denoted by a distribution of weights across these dimensions. So you don't have a one-to-one mapping of dimension. So that's where you lose some interpretability, like what does the dimension mean? You may not know that you knew earlier in one hot and also distributional vectors. So now it's spread, right? So the representation is spread by using this sparse and dense vectors, by using these dense vectors. And each element will contribute some aspect of the meaning. You can think of each dimension as some topic, like how relevant this word is to the particular topic, or some concept, a linguistic concept, and so on. Okay. And what was interesting with word vectors is that we were able to use them for various interesting reasoning tasks, right? Like various syntactic and semantic regularities were captured in a very simple way, and how simply as vector offsets. So what was found, for example, for singular plural relations, you take two words, say apple and apples, and let's say X apple is the embedding of the word apple, X apple is the embedding of word apples. So if you find the offset of apple and apples, this would come to be very similar as the offset of car and cars, right? And same with family and families. So that means the offset of the vector was capturing the notion of the relation. It was capturing the relation between the words, right? And that was very, very interesting because they were not directly trained for this task, right? So they were used for, say, analogy question. Say A is to B as C is to what, man is to woman as uncle is to what. So how would you solve it? You will simply say, okay, I have the vector for woman minus vector for man is very similar to vector for X that I want to find out minus vector for uncle, right? And what is vector for X? You will say, okay, similar, it's very close to woman minus vector for man plus vector for uncle, right? Now what you will do, you will find this vector and compute its similarity to all the vectors in your vocabulary and find out whichever vector gives you the highest value. So again, example of, say, gender, king, queen, uncle, aunt, man, woman, singular, plural, king, kings, queen, queens. So coming back to the analogy, so man is to woman as king is to what. So what you will do, so this is, so vector for, so if you have A, B, C, so what is the vector for D? So we will say vector for D is nothing but B minus A plus C, right, that we did in one of the previous slides. You find its similarity with all the vectors in your corpus and take whichever has the highest value, and you would typically find the vector queen for this as the answer, right. So this was something very, very interesting that was found with the word vectors. So now we will talk about learning them in the next lecture. So you can look at this chapter 6 of our SLP3 book for learning more about these word vectors. Okay. Yeah. Thank you.